Started pretty soon if you guys could take your seats. All right, lovely. All right, hi. So we just finished up our developmental seminar, and I'd like to introduce our artificial intelligence seminar. In particular, speakers are going to be David Ha and Kathy Wong. So let me get that started for you guys.
Okay, great. Cool. Yes. Okay. So I will be kicking off this talk by talking about one perspective. I think that will be actually really nicely complementary to what David will be talking about on how we get human-like meaning out of drawings. As Judy said, I'm a member of the computational cognitive science group. So I'm going to be coming at this from more of a cognitive science perspective, but I think it's one that, as we'll see, has a lot of implications for representing drawings to computers and representing drawings in ways that are really useful and complementary to AI systems. But the thrust of this talk is really about people. What I'm actually interested in relation to this workshop, right, is how we get and we can assess the kinds of meanings that human beings get out of drawings like these. And so I grabbed a bunch of these drawings from this Quick Draw website, which is this gigantic data set that Google's put together, in which real human beings are asked to tasked with quickly sketching various objects. And you can probably have some guess about what these objects are. And they do so until someone on the other end can figure out what they are. And so my question is here, when you look at a drawing, when a person looks at a drawing like this, how do they make meaning out of these lines? And also, I think you could ask, how do we actually get human meaning out of sets of drawings that are, deeply related in some way, right? I think you can see that there are kind of these important key semantic relationships between not just that exemplar drawing that I've put up top, but also these other related drawings that are below. And of course, I think beyond that, as cognitive scientists, we have the scientific question, right? How do we even probe what it is that a human being gets out of these drawings anyway? And so there's a variety of probes that I think both in AI and in cognitive science have been proposed. And these are perfectly valid, active ways that people will try to assess what people think about these drawings right now. One of the most basic ones is you can just put two up and ask people to rate their similarity, right? You get some single scalar score. How similar is this? Maybe on the right, I'll put a track. How similar is that? But maybe you want something a little richer, right? You understand that you get a semantics, some kind of meaning out of this. So another option is to ask people for a label. This is kind of what powers, the image classification, learning representations and networks that we've seen enormous success back in 2013 and beyond. But maybe you want something richer, right? You understand that humans see more than just a single label for this drawing. And so one really rich way that you can start to probe into this is ask people to label some kind of features. And I've kind of labeled this as if it's a bit of a segmentation task, like you're picking out these kind of semantic parts of this, but there are tons of other features I could ask you about this, right? Is it rectangular? Is this something you find around the house? I can kind of play 20 questions with the representation that's in your brain and try to probe what kind of a representation you have of this drawing. But in this talk, I'm going to suggest that there's another way. That's maybe one of the richest tools that we have to understand what is in this drawing, and that's just to ask them in natural language. And when you ask someone in natural language, right, describe what is in this kind of picture. What is it that makes this kind of particular readout of what's in your brain so valuable? And when you get this kind of readout, what is it about what language tells us about how you think about this image? That suggests the kind of representation we might need for a human-like representation of this drawing, especially if we're talking about machines, right? We are not just descriptivists here. We're not content with just looking at this kind of subtitle. How are we going to come up with some kind of representation that's going to let us bridge drawings and language? And this is something that I'm excited to talk about with David later, because I think we have different priors here, actually. So that's going to be the core of this talk, how to represent the content and meaning of this drawing so we can relate it intuitively, I think, to the meanings that people are picking out in that natural language. So let me just point out a couple of things about this language that are going to be hints, I think, as to the kind of representation we might be looking for when we're looking for something that talks about how humans think about this drawing. Maybe the most important fundamental thing that language suggests is that we aren't just seeing a set of pixels, and maybe we aren't just seeing actually just like lines, right? We're not seeing the movements of a pen, or maybe that's not the only thing we see. If you look at these kinds of words, and I think the most natural way it is that humans refer to a drawing like this, I think there's a really powerful suggestion that we decompose an image like this into this kind of compositional abstract structure. And every one of those words matters, right? Compositional, what do I mean? I just mean that we use these words that are not kind of iconic words for this single image. It's not just that there's a single one-to-one mapping between this particular pixel array. I can take a word like dresser, I can take a word like drawer, I can addend it to 2 drawers, I can qualify that it's a rectangular drawer, and I can talk about all these little parts. And that's something that generalizes beyond this particular image to all that set of images that I showed before, right? They also have drawers, many of them had knobs, some of them had feet. It's also abstract in just some very basic sense, right? We're not talking about pixels, we're talking about some higher level representation that can ground out in actually a lot of different kinds of drawers and dressers and knobs. And it's structured, right? Language, this is not just a bag of words or an arbitrary set of tokens. There's a real kind of meaning and syntax to how these words are getting combined. Yeah, so how do we get a representation like that in describing that pixel image, that drawing? So what I'm going to suggest here is that a rich line of work that's actually been explored in both cognitive science and AI is at least part of the answer. And the core idea here is that one way that we can explain and represent drawings is actually by this notion of de-rendering them. De-rendering, what is rendering? You take some kind of program, right, a graphics program, and you turn that into an image like a Pixar animation or a Blender graphics or a CAD graphics. De-rendering is attempting to be the inverse of that. You take that kind of pixel array that you see in the world and you turn it back into something that's structured like a program. And there's a rich line of work that has looked at this for a variety of images to explain both how humans actually think about and generalize across images. So on the left, there's work from our group showing how people generalize between different kinds of characters, written characters that they've seen before. And the core is that we aren't actually treating, there's a lot of evidence that people don't treat this as a single kind of similarity task, but they actually think of it as composed of these structured parts. This line of work has been taken both in an AI direction, that's the central work that I'm showing, in which we talk about generalizing these kind of like LaTeX style graphics diagrams that have real repeated structure, right? I think if you were to look at this image at the top with the 1 circle and a square, the 2 circles and square, 3 circles, squares, you can see this kind of fundamental, almost program-like pattern. If I were to keep going, you understand that I should go to like 4 circles and squares, 5 circles and squares. And all the way on the right, there's some work showing that, this actually explains a lot about how people learn about structure across sets of programs. And so depending on the kinds of images that you saw, we can really explain a lot about how you're going to choose to even down to the motor program used to draw your hand to draw these programs. It doesn't look like we're thinking at the level of pixels. It looks like we're thinking about something like skewers in the top for people who've been trained on skewers, at the bottom, this like abstract notion of circles and lines, right? So I think that's part of the answer. And why do we want to use programs, right? What is backing this kind of hypothesis that the way I think about this drawing is de-rendering it into something like a mental graphics program? And I put up a little example graphics program of this is like a pseudocode sketch, I think, of the kind of program we need here. Well, I think the core idea is that that's really language-like, right? A graphics program has a lot of properties that many people have long hypothesized suggest why it is that we produce language in the way that we do. It explains how drawings were generated, but it specifically does so by composing these kinds of abstract functions that I could use and kind of modify to talk about how I generalize across other programs. If I take this kind of dresser function here, right, it has all these arguments I can change. I could imagine what would happen if I set that end drawers from 2 to 3. It should have this like kind of like tall, weird drawer. And it's parameterized by its subcomponents and parts. I can imagine what would happen if I switched out rectangle drawer to like another kind of drawer, like a circular drawer. It's kind of a weird 70s mod thing, or like a square drawer, right? But here's the second part, I think, of the hypothesis that's really important about this work, especially talking about the specific kinds of representations that we think that humans get. It's that this is actually a representation that also lets us bridge not only from drawings to some kind of human readable or computer interpretable representation, a program, but also that fundamentally is like most well poised to let us bridge between language. Because the second part of this hypothesis, and this is a big part of formal semantics, I think a very classical line of work and how we talk about getting meaning from language that grounds out in the world, is that people also then go and talk about these drawings, not just by kind of transducing pixels into language, but actually by doing something like a translation process, right? I have this mental graphics program in my head and I translate that into words here. I might translate it into English, but perhaps there's a way I can translate this in Spanish or Chinese or any other language, right? And so that's, I think, the core part of what I want to explore here, right? It's not just going beyond those three cognitive science work exception in the past, where we've talked about different kinds of programs that we could turn those images in. I think the kind of programs we're interested in here are ones specifically that are human language-like, ones that best explain how that particular language that someone said out loud was generated by some kind of simple, straightforward mapping from those graphics programs that compositionally explains how you produce that language. Yeah, and so I think there's kind of a deflationary thing that might be lingering in the back of your head, and if it isn't, it probably should be, which is like, if you're talking about AI representations, do you actually want to get human language-like meaning from drawings? Because there are actually a lot of different descriptions in English that are technically true of this image, right? Someone could say this kind of nice sort of semantic description of how this dresser was made, but it's also perfectly true that they could describe it kind of with this very high level, abstract, and actually largely non-compositional description, right? So I realized when I was looking at this that this looks a lot like the IKEA Hemnes drawer, right? And that's kind of not going to be a representation that in some intuitive way is going to be appropriate for explaining what's related between this dresser and all those other different dressers that people drew. It seems like that's like not the right thing to say if you wanted to generalize across those images. And also it's perfectly fine, right, that I could talk at a much lower level. These are actually still compositional abstractions. They're above the level of pixels. They're telling me that I need to take a line and compose it with the notion like the vertical adjective and that it's long. And yet this also is kind of missing something I think about what feels natural about how to think and talk about this picture. So when am I supposed to end, just so I know in my head?
Let's say by the hour.
Okay,
we can
great.
have a little more time.
Sweet. Okay, then we're doing great. And so one kind of cool cognitive science work that I really want to dig in here is this claim that actually draws on another line work when we talk about what it is that people naturally like to talk about, and maybe that actually points to something more fundamental about how we like to think about drawings like these, especially in the context of other kinds of drawings, right? Which is actually that the way that people want to talk about drawings, if you just interrogate them way, is in terms of these really meaningful subparts, and specifically not arbitrary subparts, but these kinds of components like drawers and knobs and feet that have some sense of decomposing this drawing into these efficient, reusable compositional parts. And so what do I mean by that? Well, actually, the graphics program hypothesis that we've kind of been exploring throughout this talk gives us one really formal way to talk about what a good representation should be. If you look at something like, right, there is a graphics program, presumably, that I could write down. And in fact, I saw a bunch of them used to generate kind of these CAD programs in the IKEA drawer, the IKEA catalog when I was looking this up, that actually looks something like that to drawer, Hemnes drawer sentence, right? If that's actually what you said, then this is kind of the program that we might suggest you're thinking about in your head. And how do you actually take a program like that and make it executable, make it so that you can render something like this drawing here? Well, I would argue that it probably at some point looks like defining this kind of background utility function, right? You can't just run a function like Hemnes drawer. Usually, for all the programmers out there, that you have to define kind of often at the top of your file, you might abstract out this like library of utility functions that gives meaning to that particular function. And so if you want to use a token like call Hemnes drawer function, you need to go and define that in the background. And to give a picture of like what might that function be, right? I think the kind of just to make it clear, the kind of program that we're talking about here and that has been used in all of those cognitive science programs in the past is kind of this noisy probabilistic program that's capable of explaining the kind of noisy strokes that you see here. So it starts with kind of a high level structure, but it adds a bunch of probabilistic noise. And it's actually a very, very rich representation. That's what you're going to need, right? And then let's say you want to go on and explain the rest of the quick draw data set, right? So you see a new drawing like this. kind of critically, you can't actually describe that as Hemness drawer because it's not the Hemness drawer. And so you're going to go and have to like define another IKEA drawer function for this, right? And I looked it up, it seems like it kind of looks like the Helmer drawer, but don't quote me on that. And then, of course, across the rest of the data set, if you kind of extend this, this line of reasoning and how to represent this particular image, you actually might go and do something like define a single function for essentially the rest of the IKEA catalog or some generalization of it for every single one of these different images that people drew when they saw this label. And you're going to start to see, right, there's kind of a fundamental trade-off here that we are not the first to explore. To be able to go ahead and write this really, really short and in some way, right, short, efficient program for each drawing. It lets you say this really short sentence for each one of these images, Hemness drawer with 2 drawers. In the background, what you're making reference to, of course, across the set of these images is this large and in some way not very reusable library of utility functions, so very complex background parts, right? And if I were to take the other tack, right, the line and circle, now I've got this incredibly short, simple library of definitely reusable pieces. Not only can you go and draw these drawers, but you can probably go and draw the bench, the radio, right? But you have to write these incredibly long and kind of detailed programs for every drawing. And so fundamentally, right, there's actually thinking about these kinds of drawings in terms of this mental representation, in terms of composable, reusable parts that start with this kind of utility database of library functions over their parts, and then composing the programs. You can see that depending on the parts that you choose to carve up this image, you're making a different trade-off. You're actually making a different trade-off between how many kind of pieces go in your background library and how big that is, how long it's going to take you to write that one, and then how much time you're going to have to spend writing this kind of mental program, composing this mental program to talk about every single new drawing and then eventually render that into words. So in some work that I've done with a bunch of folks, really a huge collaborative effort, we actually asked, right, how is it that people prefer to decompose drawings in language like these? And so what you're seeing is kind of this caricature. They're not full drawings. We actually just went right to kind of these extremely iconic graphics programs. And we actually went and wrote down a range of candidate libraries, starting from that kind of span this trade-off spectrum. Ones that start with require very long programs to describe any one image, but have a very short background library of kind of basic level parts, all the way to ones in which, there's essentially a single program for each image. You can write these incredibly short programs that just render every example, but you've got this gigantic library. And then you can go and ask people to describe these images, and critically, right, they're looking at that image, but they're aware of the background distribution of kind of other objects they're trying to name. And you can take each one of these kinds of programs in turn, different ways of carving up that image, and ask, if I were to just fit a translation model between kind of a held out set of these programs and what people actually said, and ask which one actually explains and generalizes best to kind of English language, which of these different libraries, and therefore the programs that must represent these various images, is best for explaining what people say. And what you see, so I'm just going to zoom in on one of these kinds of sets of drawings here, the nuts and bolts that you saw, but there's actually 4. So along the x-axis, what you're seeing on the left is programs written on this very low level library, lines and circles. And so you need a very long program to describe any given drawing, but a very short library. And the other extreme, right, very short kind of exemplar programs, but long library for each. And if you look at the dashed line, what we're plotting is kind of this model-based joint efficiency cost. It's not just how long it takes to express any one program, it's actually a combination of how many elements are in the library, so how big your background mental lexicon is, and on average, what the length of any particular program to describe these distribution of nuts and bolts is going to be. And so what you see is that, like, by definition, the way we construct this library, somewhere in the middle, not at either extreme, there's this just right library, the one that's like most efficient in this very formal way. And that here happens to be L1. And what you see is, like, if you take the programs written in that library and you just look which one of these best explains the language that people say, there's kind of a clear there's a clear peak here, right? It turns out that this most efficient mental representation, in some sense, for this distribution of drawings is the one that actually best explains, that gives you the highest translation accuracy to the human language that people actually said. I mean, in fact, this is not specific to that particular domain. We actually generate these 4 domains of very compositional drawings with different kinds of parts. And you see this trend in every single one of those domains. So on the dashed line, right where you see this kind of apparent trade-off between representations that are most efficient, that are lowest in the dashed line sense, you see the peaks on the solid line. Those are the libraries that best explain the language that people actually want to see. And I want to just finish this off and say, right, like, what does this have to do with AI systems? You might already begin to see where this is going, right? But in fact, one way that you can think about drawings, and so here I have these kind of structured CAD drawings, but I think that you could take an approach like this to talk actually a lot about, the quick draw type drawings, and in fact, some folks have done that, is by thinking of them in terms of AI models that actually try to write programs based on either looking at an image, or maybe by looking at an image in a language description, by doing that inverse de-rendering problem, finding the program that actually can render them. And what we would argue, and in fact, what we've done in some earlier work, is actually take that same approach that we just talked about and show that you can kind of automatically discover and learn those libraries based on the ones that, not arbitrary sets of components, but representations that best translate into the language that people use. And we find that those are actually the ones that really compose and generalize well to actually work in real systems that kind of discover new programs to explain all these tasks. So how do we get human meaning out of drawings? To sum up, the argument of this work here, right, is that human language offers this really powerful window into thinking, into how we actually think about these drawings, what their content is. And it suggests that we think of them in terms of these really rich structured compositions of these abstract parts. Here, we've suggested that there is kind of an explicit representation of graphics programs that offers this really human language-like substrate for modeling these kinds of drawings. And specifically, it talks about kind of this background set of abstract components that are just composed on the fly into programs that render each one of these images. Now, cognitive science work, like the work we've done and that others have done, really suggests that when the kinds of representations that we talk about in our own human language, they're not arbitrary, they're actually really efficient. They're efficient for representing these images. And so we can use those kinds of representations actually to be efficient for AI models too, that generate drawings, that understand images, and that generalize across a variety of tasks. So thanks. This was work that was done with a huge number of collaborators, and I'm really excited to kind of dig into this in the portion after this.
Thank you so much for the lovely talk. I see a hand from Wilma Bainbridge. Go ahead.
Hi, great talk. So I was wondering, you define drawings as compositions of abstract parts, but I'm curious, what about the non-part aspects of drawings, like the textures or the examples you showed were these man-made objects, but maybe more natural objects like animals or plants or rocks might not have these specified parts. And so how would you define programs for these sort of more like abstract shape objects?
Yeah, I think that's a really good question. So let me answer that in style rural parts, because I think there's like 3 distinct kind of aspects of this question. One is like, well, programs explain maybe feels like some of the content of these drawings, right? Like it can tell me this dresser and look at this dresser and say like, yeah, it's composed of like knobs and feet. And maybe even for animals and plants, I'd say, I think if you ask people to talk about it in this way, that's, it's not just an arbitrary task we're giving them. In this case, we were asking them, how would you make this drawing, right? But you can ask them other tasks, I think would elicit actually similar kind of language. Right. Christian here actually has done work on the animal domain, birds, right? We can think of them in terms of beaks and feet. And I would argue that like when someone says a bird, that bird drawing, it has beaks and feet and a wing, I think that it's not just that they're talking about something that is related to this really rich conceptual system inside their head that I think plays an important role in how human beings can represent anything from this like arbitrary sketch of a bird to like an actual bird in the world to like, a Pixar representation of a bird and understand it as kind of like, yeah, there's the beak and it fulfills some function for the bird and also looks a certain way. But I think there is this really important aspect of like, yeah, but So that's like semantic content, maybe the big part of it, but what about the like particular style and texture? What is it about this representation that's going to take us, that actually like is going to differentiate between, you know, how Picasso might go and draw the drawer and how Quick Draw drew the drawer, because there's also something different about that. I think there are ways in which these graphics programs can actually be thought of as being capable of representing and explaining a lot of variants that are richer than the kinds of representations that we looked at here, right? So I think in a lot of the work, so in the very particular work that we looked at with those CAD drawings, right, there's no variation in texture and style. Actually, in some of the work that I was trying to put up from, you know, that has actually looked at real human drawings, they need to handle that in some way. And the kinds of components they look at, so even for this like little wiggly stroke, right, there's a notion of a wiggly sort of S-shaped stroke, it's a lot richer there. There's kind of, they think of, you know, there's some kind of probabilistic parameter that might be specific to you, which helps encompass your particular style. Like if your hand is really shaky, right? Just imagine someone's hand really shaky. There's a way that we can say like, well, you're going to start with an S, but this person's style is actually like that. They have a very kind of shaky component of it. I think that's a partial answer. And clearly, I think that there are kinds of perceptual methods of thinking about decomposing this object into its parts, but then also kind of incorporating this kind of rich stylistic parameters on top. And there are a variety of representations, maybe some that actually do look more like these perceptual representations that are learned by kind of image recognition systems that might be more appropriate for that. But I think that what I would point to here is like, I think that to really explain all of what people see in these images, it's going to be some kind of, or I feel that is some kind of marriage of the two, that the graphics program is kind of explaining the like base core semantic content that we see, especially in these kinds of really structured images, but it's not all that's needed. And there are programs, you know, I'll just point to, right, like there are graphics programs that can be rendered into all kinds of styles when you know, Pixar creates different stylizations for all the different characters. Usually that starts with kind of a base semantic skeleton over kind of semantic parts, but there are, you know, there are many successive layers of texturing that come on top of that.